Hello, and welcome to the final presentation of Thermal Live 2018. I'm Murray Slovic, Senior Technical Editor with Electronics Cooling here in Philadelphia. Thank you for participating in this year's two-day online event. We've seen some really great presentations thus far, so let's keep going. Our last presentation, Phase Change Material Heat Sinks, Fundamentals of Operation and Real-World Applications, comes from Advanced Cooling Technologies, Inc. It should run about 35 minutes, and a short 10-minute question and answer session will follow. We welcome audience participation, so please locate the Q&A panel on your screen and submit as many questions as you'd like during the presentation. We'll answer as many as possible in the time allowed at the end. If you want a copy of this presentation, downloadable slides are available under the Resources tab at the bottom of your audience console. Our presenter today is Kimberly Fixie, an applications engineer for Advanced Cooling Technology. Kimberly works with customers to diagnose complex thermal challenges and develop the appropriate solutions. Without further ado, please welcome Kimberly.
Thank you, Murray, and welcome to our webinar on phase change material. In our webinar today, we will begin with identifying what a phase change material, or PCM, is, and the chemical characteristics that make certain molecules stronger than others. We will continue with the modeling and design of PCM heat sinks, and wrap up with examples and applications of these thermal management tools. Phase change material, or PCM, is any material that has a relatively high thermal capacity, or latent heat value. Latent heat is the amount of thermal energy a molecule requires to convert to a different phase. The latent heat of fusion is the amount of thermal energy a molecule or element needs to convert from solid to liquid. And the latent heat of vaporization is the amount of thermal energy a molecule or element needs to convert from liquid to gas. The graph, depicted on the right of the screen, shows a comparison between specific heat and latent heat. Now, specific heat is the amount of thermal energy a molecule or element absorbs as it raises 1 degree Celsius. You can see where the graph flattens out, that is the latent heat phase. The molecule or element is absorbing thermal energy, however, it is not raising in temperature. Now, let's break down the bonding to determine what gives a molecule or element a higher latent heat value than others. There are two types of molecular bonds, intramolecular bonds and intermolecular bonds. Intramolecular bonds are created within the molecule. Covalent bonding is a type of intramolecular bond. In covalent bonding, the atoms share a valence electron. Chlorine, for example, is an element with 7 valence electrons and will form a covalent bond with itself to become Cl2. The two chlorine atoms will share one of their 7 valence electrons in order to reach a more stable octet. Hydrogen is another example. The hydrogen atom will do the same. However, hydrogen only needs 2 valence electrons in its s orbital to reach its stable state. This will form H2. An ionic bond is one in which there is a complete transfer of valence electrons. This complete transfer creates 2 oppositely charged ions. A good example of an ionic bond is sodium chloride, or table salt, NaCl. In this intramolecular bond, the sodium atom freely gives up one of its valence electrons to the chlorine atom, who only needs that 1 electron to reach its stable octet. By doing so, sodium becomes a positively charged ion, and chlorine becomes a negatively charged ion. There's a type of bonding between covalent and ionic. This bonding is called polar covalent bonding. Like a covalent bond, the valence electrons are shared by the atom. However, these electrons typically spend more time with one of the atoms than the other. Though ions are not created, the molecule does achieve a level of polarity. The water molecule is an excellent example of polar covalent bonding. Although the electrons are shared between the oxygen and hydrogen atoms, they spend more time around the oxygen atom. The final intramolecular bond is metallic bonding. In these systems, valence electrons freely move throughout the lattice structure. Intermolecular bonds are chemical bonds created between molecules. A dipole-dipole interaction is when a positively charged side of a molecule interacts or attracts with the negatively charged side of another molecule. This would be when the positive sodium atom attracts to a separate molecule's negatively charged chlorine molecule. The molecule itself does not change. These types of bonds occur with either ionically bonded molecules or molecules with polar covalent bonds. Hydrogen bonding is a special type of dipole-dipole interaction. This interaction only occurs between hydrogen and either oxygen, nitrogen, or fluorine. These are the types of bonds that link water molecules together, which create surface tension. The final type of intermolecular bond is a London dispersion force. London dispersion forces are when electrons interact between molecules. The more molecules you have present, the larger the London dispersion force. In order to select a good PCM, we would typically look at materials with strong intermolecular forces. Those are molecules that have ionic and polar covalent bonds in order to get that dipole-dipole attraction. However, hydrocarbon chains are also strong PCMs. A hydrocarbon chain is a form of covalent bond. 4 hydrogen atoms share their valence electrons with one carbon atom that itself holds 4 valence electrons. The simplest hydrocarbon is methane, or CH4, which is shown on the slide. A hydrocarbon chain consists of the formula CnH2n plus 2. Any hydrocarbon with 5 carbon atoms or less will be gaseous at room temperature. Hydrocarbons with 5 to 15 carbon atoms are liquid at room temperature. And those with a greater than 15 number of carbon atoms will be solid at room temperature. Now, hydrocarbon chains are one of the most common types of material used for phase change thermal storage for several reasons. One, as the chain increases, the London dispersion forces also increase. That means these chains can have a relatively high latent heat value. They also can be created in a lab and therefore offer the flexibility and melt range needed to achieve the desired temperature stability. Here, we see a graph of the typical phase change materials. Paraffin waxes, otherwise known as hydrocarbons, have a relatively high latent heat value that can range from 200 kilojoules per kilogram to 280 kilojoules per kilogram. They, however, are poor thermal conductors. Hydrated salts, on the other hand, are ionic bonds and not only have high latent heat values, but also are thermally conductive. Their latent heat can range from 60 kilojoules per kilogram to 300 kilojoules per kilogram. While hydrated salts appear to be the most desirable PCM, they also tend to be corrosive and may break down or separate after several cycles. As mentioned, hydrocarbons or paraffin waxes are the most common phase change material. They are chemically compatible with most metals and have large latent heat and can be obtained over a wide temperature range. The table at the bottom shows some high-purity paraffin waxes used in many electronic applications. Temperature ranges of 72 to 76, 66 to 70, and 59 to 66 are good to ensure safe operation of many electronic devices. As seen on the common paraffin wax slide, most PCMs have a melt range. It is important to note that melt range is also a factor of chemistry. The graph on the right shows a very flat, distinct melt point temperature. But most common PCMs have that melt range. The melt range is based on the purity of a material. For example, water is often found with other molecules saturated within. Distilled or pure H2O will have a melt temperature of 0 degrees Celsius. H2O with other saturated molecules will have a melt range. Hydrocarbons are similar. The purer the hydrocarbon, the smaller the melt range. However, pure hydrocarbons tend to be more expensive, so it is important to determine the melt range your design will allow before selecting your PCM. Finally, when discussing chemistry, we need to identify compatible PCMs and envelope material. For example, water and aluminum are not compatible. If one were to use water as the PCM and aluminum as the envelope material, the two would react and create non-condensable gases. Typically, hydrocarbons or paraffin waxes are chemically stable and will not react with metallic envelopes. Hydrated salts, on the other hand, tend to react more often and need a chemically compatible envelope. We will now explore how to design a PCM enclosure. In designing a PCM heatsink, the first critical parameter is the selection of the PCM itself. The key attribute is selecting a PCM that has a melting point at the temperature that is acceptable for device operation. You can see on the chart on the right a series of materials and temperature ranges from plus ice. Several options are available. Other important parameters include compatibility with the base heatsink material, the type of PCM, and its purity and thermal storage capacity. Once potential material has been identified, they should be evaluated for storage capacity, including bin thickness and the required PCM volume and weight. In the table at the bottom, for example, 3 PCMs with the same melting point and fin volume deliver different thermal storage performance due to different latent heat and mass properties. In order to identify the size of our heatsink, we need to calculate the total amount of phase change material needed. To do that, we will use the equations energy is equal to power times time, mass is equal to energy divided by latent heat, and the volume is equal to the mass divided by its density. For this example, we will select a PCM with a desired melt temperature of 50 degrees Celsius. For that melt temperature, we have selected a PCM with a latent heat diffusion value of 168 joules per gram and a liquid density of 0.76 grams per centimeter cubed. Let's say our desired amount of power stored is 50 watts, and we need to store for about 3 minutes, or 1800 seconds. Since energy is equal to power times time, the total amount of energy we need to store is 9,000 joules. To determine the mass of the PCM needed, we would take that 9,000 joules and divide it by the latent heat value of 168 joules per gram. That leaves us with 53.57 grams of PCM. In terms of volume, we need to divide the mass by the PCM's density of 0.76 grams per centimeter cubed. That leaves us with 70.49 centimeters cubed of PCM. Because the PCM we selected was a paraffin wax, which, as discussed, has poor thermal conductivity, we can assume that an additional 10 to 50% volume would be added for the conduction surfaces. Now that we have determined the volume of PCM required, we need to address two primary challenges associated with the design of a PCM module. The first is designing around the poor thermal conductivity of a paraffin wax-based PCM. These wax-based PCMs have thermal conductivities between 0.2 and 0.3 watts per meter Kelvin. Simply filling a container with PCM and applying a thermal load would create a large temperature rise as the PCM melts. The second challenge is managing voids at the location of critical heat loads. You can see in the figure on the right, a void volume is present to allow for the expansion of the PCM during phase transition. In most cases where orientation with respect to gravity varies, the location of the PCM when it melts and freezes will vary as well. If there is a significant empty space around a critical component, that component can see a large temperature rise before the PCM absorbs the thermal load. The solution to both of these challenges is in the design of the internal conduction paths, which typically are fins internal to the heatsink. As you can see by the thermal resistance network outlined in the figure, conduction will play a large role in assuring the PCM melts without significant temperature rise. The fin spacing, or fin pitch and thickness of the fins, are critical design considerations. In the next slide, we will demonstrate the trade considerations during the design. As discussed on the previous slide, since most PCMs are those hydrocarbon paraffin-based waxes, getting the heat into the PCM efficiently is a key design parameter. Here is a plot that can be used to identify a starting point for the fin pitch and thickness within the PCM heatsink. The solid line shows the time to melt, or thermal storage capacity, for a given power on the left axis. The matching colored dashed line is the corresponding thermal gradient through the fin and the PCM shown on the right axis. Both curves are a function of fin spacing. As you can see, there's a trade-off between thermal storage capacity and delta T. As you add more fins, you reduce your thermal gradient, but displace more PCM, which reduces the thermal storage. A scenario with too few fins is shown toward the left side of the plot. At the other extreme, the spacing between the fins is large to maximize the volume of the PCM, but the gradients are large due to the poor thermal conductivity of the PCM. This occurs toward the right side of the plot. For the heat load and geometry used to generate these curves, the optimum fin spacing is between 0.05 to 0.10 inches. This is where the margin gains in the thermal storage capacity are observed as fin pitch is increased. Optimizing the fin pitch and thickness assures that all PCM is melted with a minimal thermal gradient, thereby maximizing the performance of the heatsink. A schematic of the PCM heatsink module structure is seen on the right. Internal features include PCM, fin structure, and void allocation. During manufacturing, a heatsink module will be completely leak-tight, which makes it a pressure vessel. As we touched on before, since there's expansion going from solid to liquid, the unit requires a void volume when in the solid state. Typically, this ranges between 8 to 15%. One of the challenges is assuring the void volume does not cause unwanted temperature rise, and fortunately, this design challenge is resolved by proper fin design that we discussed in the last slide. Since the fins will provide a good conduction path to get the heat into the PCM, the temperature rise is minimal, no matter if there is a small void at the large heat generating component. When dealing with high heat fluxes in discrete locations, management of molten PCM flow must also be considered in the design. Localized heat input can produce high pressure gradients as PCM melts, expands, and yields the surrounding solid PCM. Enhancing heat spreading with heat pipes, for example, can reduce this effect by uniformly melting the PCM. Flow considerations that allow the PCM to move more easily during melt have also been developed. Here is an example of a typical PCM application. In this case, after selecting the PCM, determining the required volume, and designing the enclosure with proper fin and wall structure, it's time to manufacture and test the PCM. This slide shows a tested sample with the estimated properties shown to the left. Note the large change in specific heat for the different temperatures. Specific heat, which is related to the latent heat diffusion mentioned previously, is the amount of energy per unit mass required to raise the temperature of the material by 1 degree Celsius. The reason why PCMs are so effective is that during phase transition, there's a dramatic increase in specific heat. As you can see, there is an order of magnitude increase from approximately 1,600 joules per kilogram degree Kelvin as a solid to over 60,000 as it is melting between 72.2 and 75.9 degrees Celsius. Here are the results from the test setup we saw on the previous page. As indicated by the solid black line at the top of this graph, we applied slightly over 40 watts of total power with air at room temperature. You're familiar with the blue theoretical line as shown in slides earlier in this presentation. Basically, the module heats up until it reaches the PCM melt temperature. It can then hold within a few degrees of that temperature until nearly 100% of the PCM has melted. Once all the PCM is melted, the temperature begins to rise at the rate dictated by the specific heat. In this case, the PCM heat sink was designed to absorb the heat load for about 250 seconds, with some margin. The red tested results matched fairly well, and the theoretical temperature was never exceeded. To recap, phase change material utilizes the latent heat diffusion to absorb thermal energy. Latent heat is typically 1 to 2 orders of magnitude higher than specific heat. PCM is commonly used as a passive heat storage device that provides reliable cooling for a given period of time. However, it is important to consider the low thermal conductivity with respect to the volume needed. Now, we will dive into some applications in which PCM is utilized. Many semiconductor communication devices operate in a transient on-off mode. During the on cycle, they utilize a lot of power, and the device can get quite hot. Fortunately, duty cycles are relatively short, typically between 2 and 10%. Locating PCM near the individual gates can aid in increasing performance reliability and extending the life of these devices. As can be seen in the schematic on the right, the pulsed heat source is on a GaN layer and a silicon substrate. PCM is embedded within the silicon substrate, and when the device is on, the heat will cause the PCM to melt. As we have seen, the melting provides some stability in temperature, and so very high temperatures from repeat cycles are avoided. In these applications, ensuring the proper amount of PCM, enough to absorb all the heat during the on cycle, while also being able to dissipate all of the heat in the off cycle, is important. Part of the system design should include calculation of the minimum distance between the heat source and the PCM to avoid parasitic effects. Here are some results. The high junction temperature during the on cycle is the biggest challenge in these high-powered pulse devices. As you can see in the graph at the bottom left, the objective in adding the PCM is to limit the temperature rise of the high electron mobility transistor, or HEMT, to the PCM melt temperature. The picture in the center is an application of this approach where the PCM is located within grooves that are sealed with an indium layer. The graph on the lower right plots the normalized drain current versus the pulsed width. You can see how the PCM provides a much more stable performance, especially at high pulsed widths. Our second application is heat sinks for electronics thermal management. An exploded view of these types of heat sinks is seen on the right. The red metal parts encompass the enclosure in which the PCM and folded fin assembly are located. The design process block diagrams detail the key individual steps. First, the transient heat load power plus time is established. This determines the required PCM reservoir sizing. There is then the iterative design sequence, reviewing fin design and over structural analysis that ultimately results in the final design. This transient thermal modeling will confirm the heat transfer to and from the PCM, identify the location of the PCM melt front over time to ensure adequate PCM is present to handle the full transient load, and the overall system delta T to make sure the device is not overheating. Let's look at some results with this kind of design. Here are the results. In the graph on the right, the dotted red line represents the heat load profile. The heat load is on at the beginning of the graph and drops down approximately 200 seconds into the cycle. The blue line represents the PCM heat sink temperature, and the black represents the ambient temperature the device is experiencing. One can see through the varying heat loads of the dotted red lines, the blue PCM remains relatively constant and at a slightly higher temperature than ambient. The relative rapid rise of the blue PCM at the end of the graph is an indication that all of the PCM has melted and could be in a runaway condition. Fortunately, in this case, the on-cycle has ended and the PCM will begin dissipating heat. On the right is a schematic of a melt front for a single folded fin. The red heat source is on top, and the melt front, that is the edge of where the PCM is undergoing the solid to liquid phase transition, is located at the yellow to green color transition. It is, of course, important that the melt front move. In our third example, we would like to step beyond a PCM heat sink and consider a PCM heat exchanger. Like with the heat sink, addition of PCM can enable sizing of the heat exchanger to be based on the average power rather than the peak power. The concept here is that the PCM exchanges heat with both a heat source and a cooling loop that is tied directly to the ultimate heat sink. PCM temporarily stores the thermal energy and slowly releases it to the ultimate heat sink. The ultimate heat sink can then be reduced in size and weight regardless of what type of system. Some examples include reducing radiator size in space applications and reducing convection heat sink volume in terrestrial ones. In this example, we'll show the effect on a fluid heat exchanger that couples a liquid cooling system with a vapor compression system. In this specific application, the heat exchanger is for a directed energy weapon, but is applicable anywhere that significant pulse mode operation is present. In this case, operation is typically less than 40%, which allows for a mass reduction in the entire system. The schematic in the bottom right corner represents a sample DEW system. Here, the high energy lasers, or HEL, were cooled with a deionized water loop, which is depicted in the bottom of the schematic on the lower right. The vapor compression loop, seen at the top of the schematic, is where the heat is ultimately rejected during the off times, with an air-cooled condenser. The PCM heat exchanger couples and transfers heat between the two loops while also dampening the pulses from the high-energy lasers. The design considerations for this system are similar to the heatsink modules, where one must determine the volume of the PCM required to absorb the power over the duty cycle, and then design the system with enough PCM surface contact, in order to reduce conduction gradients throughout the PCM. The final example is a safety mode, or limp home survival mode. In this case, the PCM is used as a backup cooling system if the design loses cooling. Here, a PCM heatsink is designed to absorb thermal energy during the 30 minutes it takes for the design to return to a home base. As the critical components lose their cooling, their temperatures will rise, as seen on the graph to the right. The PCM will begin to melt and absorb the thermal energy so the components do not fry as the design returns to its base. Phase change material utilizes the latent heat diffusion to absorb thermal energy. This technology works as a thermal battery or thermal capacitor. The design of such systems depends on the type of PCM selected and the parameters surrounding the need for cooling. When selecting a PCM, it is important to note its chemical structure, which will determine the latent heat and melt temperature of your PCM. It is critical that the internal structure of a PCM heatsink is compatible with the selected PCM, whether it's with the chemical compatibility or the internal fin structure, to ensure a constant melt throughout. This type of thermal management tool can be used in a wide variety of applications and continues to grow in popularity. Applications such as on-chip cooling, electronic heat sinks, heat exchangers for directed energy weapons, power plants, and single system uses, to name a few. I want to thank you for attending this webinar and encourage you to stick around during the question and answer session immediately following. Thank you.
Thank you. For our audience, if you haven't already submitted your question, now is your opportunity to enter them into the Q&A panel. The question and answer session today, we'll have Daniel Fritsch helping out. He's the lead engineer in the Defense and Aerospace Product Development Group at Advanced Cooling. While there, he has developed numerous custom thermal management products ranging from phase change material heat sinks to custom fluid control units for ground testing of spacecraft payloads. Through his work at the company, Dan has gained experience in advanced cooling strategies for embedded computing, power amplifiers, and directed energy weapons. Along with his work in product development, he has also contributed to several programs involving computational fluid dynamics, pump two-phase cooling systems, and phase change materials. We have a number of questions that have come in, so let's get right to them. First question from the audience: do PCMs suffer from aging? What are the material characteristics that deteriorate?
So this is kind of it depends on the PCM. So organic paraffins, especially pure components, typically do not suffer from aging problems. We have them currently in products that are meant to last for up to 30 years. Hydrated salts are known to typically lose some of their latent heat characteristic over time, just because they have some kind of loss of water from the hydrated salt, so it doesn't recombine quite the same each time. So I think both the melt temperature can change slightly, and definitely the latent heat can change over time. But typically for longer lasting systems, we try to incorporate organic paraffins when possible. And then high temp PCMs like metals don't really change very much either.
Mm-hmm. Our next question is, what's the maximum wattage for which PCM systems have been designed?
This one also kind of depends on the scale that you're talking about. We have built heat exchangers that are meant to take in up to 100 kilowatts of power. That's like a liquid to PCM heat exchanger. Then we have small phase change material heat sinks that go directly onto electronics. Those can be up to a couple kilowatts, depending on the size. It more depends on the heat flux, I would say. Typically, we're trying to keep it under about 5 watts per centimeter squared or so, but we do have abilities to go above that, integrating other technologies like heat pipes.
Listener Katie wants to know about example applications. She asks, what industries commonly use PCMs? Do you have any example applications?
Sure, I can't identify all of the industries that use them, but we use them pretty heavily in the defense and aerospace industry. So this is basically cooling electronics, PCBs, RF antennas, various different high heat generating components or duty cycle components. We've also used them in energy production industry. So there was for like renewables, it's useful for storing thermal energy in renewable energies. So solar industry has used it. Also hydro industry. So, and then like wind energy has also used it, I believe.
Our next question is there a guideline for how much additional volume needs to be allocated to compensate for the solid to liquid phase transition?
Yeah, I think this was mentioned briefly in the presentation as well. I think there was a guideline given of about 15 to 18% extra volume to account for PCM expansion from solid to liquid phase. I think that's a pretty good guideline for this time, but you can look up the individual densities of the solid and liquid of each PCM, and you can kind of determine the extra volume needed from that.
Mm-hmm. Our next questioner asks, how do you incorporate contact thermal resistance?
So this, I'm not sure if this refers to contact thermal resistance between the heat sink and the PCM itself, but we typically do not worry too much about the contact resistance there. We're more worried about the contact resistance between like a chip and the housing or the enclosure of the PCM heat sink. We don't find that the thermal resistance in the PCM itself is a big contributor to the overall thermal resistance.
Mm-hmm. That concludes our question and answer session. That's all the questions that we have. I'd like to thank once again Kimberly for sharing the wonderful information with us, and to Dan for handling the questions. All the questions submitted will be posted on our website with answers. So if we didn't get to your question, or if it came in late, you'll be able to find it there. You'll also receive an email with a link to the on-demand version of this presentation in about 24 hours. Before we go, it's time to announce the winner of this year's 2018 Thermal Management Product of the Year contest. Congratulations goes out to Harley Thermal for their submitted product, Solaris. More information can be found on the ThermoLev website. That wraps things up for ThermoLive 2018. It's been a pleasure hosting this one-of-a-kind event for you over the last 2 days. I'm Murray Slovic on behalf of Electronics Cooling. Thanks again for participating in ThermoLive 2018.